The Cyber Resilience Act, or CRA, is no longer on the horizon. It's at the end of the street, and many connected device manufacturers still lack a coherent implementation plan. Unfortunately, cybersecurity isn't as simple as integrating a software library or soldering an extra chip on the board. It demands a holistic approach that covers expertise, processes, and infrastructure. So what solutions are there that go beyond just the silicon that can meet the cybersecurity lifetime demands of CRA? I'm Stuart Cording, the electronics reporter, and in this episode of Mauser Talks Tech, I'm talking to Tim Scherer, Senior Embedded Solutions Engineer for Cyber Resilience at Microchip Technology Inc. Hi, Tim.
Hey, Stuart. Good to be here with you today. Thank you for the invitation.
You're welcome. Now, I already mentioned the CRA, or Cyber Resilience Act, there in the introduction, and that's really focusing minds on implementing proper cybersecurity. Can you give us an overview of CRA and perhaps more importantly, what it encompasses?
Sure. So at a very high level, the Cyber Resilience Act makes cybersecurity a market access requirement. So without following the CRA, without having the CE marking on your product with digital elements, you're technically not allowed to sell these devices into the EU market anymore. The deadline is next year, December 2027. However, we will talk about this later, I believe. The reporting obligations will also kick in.
Now, what is the scope of applications it applies to? Is it just internet-connected devices?
No, so the application is actually very broad here. It talks about products with digital elements. So any product with having a direct or indirect connection to another device or a network is actually in scope here. So technically, think of a vacuum cleaner, a robot vacuum cleaner connecting to your cloud. It's in scope. Industrial sensor in scope, and even software is in scope here. So we can look at it from hardware only, software only, or combination of them. And also, remote data processing solutions are in scope here as well. So a cloud talking to your connected device would be in scope as well.
That's exceptionally broad, and I hadn't realised that the scope covered software as well as software running on hardware in IoT type devices. So that is probably a surprise to many as well. Now, in the same sentence as CRA, we often hear mention of various types of standards. There's the ETSI EN 303645, and there's also the IEC 62443. How do those standards relate to CRA?
Okay, yeah, very good question. When we hear about the EN 303645, it is more consumer IoT related, and it acts as a baseline standard, while the IEC 62443 standard is more industrial cybersecurity focused. However, and now comes the magic of the CRA into the game, we have harmonized standards, or we will see harmonized standards here. Harmonized standards are then again split into vertical ones and horizontal ones, where the horizontal ones are more like framework related, and the vertical ones are more product related. So we have a product scope. Look at it as the horizontal ones are the framework where the verticals can build on. One horizontal one is, for instance, the vulnerability management. We will hear the 40,000 series in the future. The 40,000 series is exactly this framework. Whereas the vertical ones, for instance, when we talk about microcontrollers with security-related functionalities, or even boot managers, so really product specific, where the scope is narrow, we have other standards coming from, for instance, ETSI or Sensenelec.
Now, I understand that the full compliance with enforcement of the CRA is planned for December next year. That's 2027, as you already mentioned. So, why is it that manufacturers don't really have a lot of time to get to grips with this?
Yeah, so I wouldn't say they have plenty of time. Actually, they should start already today. No, better, they should have started yesterday, because as we as we learned, the full compliance kicks in next year, December 2027. And when we think of the CRA, it is not only a security checklist. No, it is fundamentally changing the way manufacturers should think about cybersecurity, how to implement it, and it is a lot about change management, of course. And also, we do not only look at the product security requirements anymore, but we look at the whole product lifecycle. So from the design, buzzword here would be security by design, secure by default settings, to the lifecycle, even beyond the manufacturing phase, we look at the end of life phase. So how can we make sure that once you sell the device, once it's not in the field anymore, you can reset it into a state where the security and the safety is not at risk.
So obviously, there's a lot to that. Let's start digging into the implementation details for those people who really have an internet connected embedded system. Now, assuming there's no cybersecurity beyond that which is integrated into an existing physical layer. So let's take, for example, Wi-Fi communication that already has its own cybersecure communication method. What else do I need to be looking at?
Yeah. So I would simplify it into 4 core building blocks here. If you want to like make your device secure in a way that it has a firmware validation, secure part, and some crypto operations. So the number one would be you need to have a trusted boot chain, because you want to verify what is running on your device. You don't want to have anyone else uploading your compromised firmware to your device. With that comes the second part, the second pillar, which is firmware integrity. So if there's an update, you want to validate that it's not tampered with, and you want to verify what is running there. The third one is security and key protections, because once you have crypto on your device, you want to make sure that the keys, the root of trust, is secure, that no one can change the keys or can read the secrets on the device. And then the fourth pillar is you're not always needed, depends on how sensitive the data is you're handling with, would be encryption, robust cryptography here. Because if you have sensitive data, you want to make sure that they are encrypted at rest, and also in transit here. And that said, you also should look at the intended use of your device and the risk associated with that device. So having a risk assessment is one of the most important things you should do as a manufacturer preparing for the Cyber Resilience Act.
Now that sounds like a great starting point, obviously, in terms of planning. At some point, obviously, we need to get to some sort of solution, a chip. A Microchip offers a wide range of cryptography solutions that deal with a lot of the digital complexity and ensure that security. What are you recommending your customers for these types of applications, and why are you recommending them?
Yeah. So the secure element, for instance, for Microchip, we have the ATECC 608 or the TA100 series here. These are secure elements, dedicated secure elements, which naturally maps to those 4 building blocks I talked about. So with those devices, you can implement cryptography, you can enable secure boot capabilities, you can also run firmware over the air update infrastructure with it, or firmware over the air update capabilities, and managing keys and certificates in the field. All of this comes with a very secure pre-provisioning of the devices, which makes it easy for the manufacturer then to work with these devices and to have a secure environment set up easily. So the value is that it gives your system a root of trust, which you then can build on.
Now, you mentioned in that answer there the keys. The keys are obviously a key element, or the most important element of implementing the security, and those keys need to be protected. We've heard stories about people finding sort of default keys in open source software for automotive applications, for example, and then anybody can sort of attach to the system using one of those keys. How does a developer actually achieve that key protection in a resource constrained microcontroller?
Yeah. So think of let's stay with the secure element ECC 608 here. Think of the secure element being a secure vault in your hardware. So it protects the key on it. No one can else see the key, can read it, and you as a developer then, what you need is a host controller, a host MCU talking, for instance, via the I2C bus with your secure element here. So you have a secured connection. You can even encrypt this connection through further cryptography in place. But one important thing, and this brings a lot of confusion sometimes, is how can a host controller communicate with the secure element? It's actually pretty easy. You have a challenge response capabilities here, challenge response mechanisms. So the secure element sends a challenge. No, other way around. Sorry, the host MCU sends a challenge to the secure element. Only the secure element can then answer, and with that, you would transfer secrets via this challenge response mechanism here. And yeah. What else? The secure element contains the key storage for sure. It contains the crypto engine, the true random number generator here. And of course, you also need software to communicate with the secure element. And I talked about having the firmware over the air update capability here. You need dedicated libraries, which we can deliver, of course, and which makes it easier for the developer to communicate it. It's standard C, it comes with Python APIs you can work with, so makes it very comfortable for the manufacturer to use it in the field and in the prototyping.
That's a very good point you raised there, because I've, like many of our viewers, have developed software for embedded systems, and typically there's a process where you edit the code and download it multiple times an hour sometimes in order to try and fix a problem or try and resolve some issue or improve the design of the software. So you've said that obviously we need that cryptographic authentication so as that we know we're running a proper image, maybe a secure bootloader as well. Can I continue my old development process and then just add the cryptography and the security, cybersecurity, right at the very end when I'm almost finished?
Yeah, you can sometimes add pieces later. However, it is not always recommended. It really depends on what are the prerequisites you have already in place. So what is the host MCU capable of delivering? And what do you actually want to achieve? Now, specifically from a Cyber Resilience Act perspective, I named the essential cybersecurity requirements, and I linked to some of the harmonized standards talking about different use cases as well. You really need to look at, what do I need? What is the intended purpose? What is the use case here? And then, of course, you can add security on top of your existing PCB, on your existing design. However, and that's the main idea from the CIA, for new devices, for new projects, think security at the very beginning of the stage. So having the security by design in mind. So if you're now looking at doing a revision of your device or of your design, then come to us, talk to me. We can then discuss this better and look what is your use case, what do you need, and how we can bolt on security later.
Now, obviously, as you said, ideally it should be done right from the very beginning. And in order to do that, personally, I'd want to try and get my hands on an ECC 608 and actually try this out and figure out how it all works, so as I understand in isolation what needs to be done. How can someone get started with a device like the ECC 608?
We do have development boards. We have evaluation kits where the ECC 608 is already part of the evaluation kit or the dev board, as we call it. For instance, the CryptoAuth Pro Trust Platform, EV89U05A. That's like the part number, the long part number here. And what we have on this device is the MCU as the host controller and multiple secure elements, ECC 608. Some of them are already pre-provisioned. So when we talk about the Trust Manager, they come with a pre-installed birth certificate, making it easier for the initial bootstrapping of device keys and secrets to communicate with your cloud. And of course, having access to our Trust Platform Design Suite software, you can also use this to configure further keys, to upload certificates, to change settings on the ECC 608. So my suggestion is, if you want to get started with a secure element such as the ECC 608, go and buy such a development board and you're ready to go.
Now, it's great, obviously, that those sort of birth certificates are already there in those devices, pre-provisioned and ready to go. So that gives me the opportunity to figure out how to work with them and integrate them into the prototypes I'm developing and ensure cybersecurity is there from day one of development. Obviously, the next step is when my product's finished and I need to move it into manufacturing. How do we go about then in a mass manufacturing environment, getting the programming keys and certificates into those devices? What sort of approaches and options are there?
Yeah, so that's when the real complexity kicks in your how you organize yourself, how do you handle all the keys and the certificates. It can be really complicated, depending on how many certificates and keys you need to manage later. Because if you have an IoT sensor device and you want to connect it to an AWS or any other cloud, then for sure you will need certificates eventually. Now you asked, how can a manufacturer handle all of this? So there are two options. Either you do it on your own, which is costly in terms of buying and getting the devices you need to securely store all those keys, to manage them. You need user management, you need key storage, an HSM. So everything is not so easy to implement on your own if you're not comfortable with it or if it's not your daily business. Or you can choose a service provider for that. So in terms of Trust Platform Design Suite, we have an add-on, which is called the Trust Manager, which is a solution as a service, giving you access to a fully HSM, so a full HSM, storing your certificates, handling your keys. You can log into this environment. You can start creating your first root CA and onboard all the devices. So how does it work? If you buy secure elements from Microchip, you decide early in the stage that you want to have, for instance, the Trust Manager capability. We will generate dedicated product names based on the ECC 608 for you, which are then linked once you start the device to your user account. In that step, the bootstrapping starts. The user certificates will be uploaded or downloaded to your secure element. And then you can start you can start provisioning further certificates needed for your AWS cloud, for your Google Cloud, or whatever application you are running on top of it. That's the way how you do it. So either do it all on your own or be more flexible, which makes it easier for scaling and gives you less burden of handling it on your own.
So we've got Trust Manager there on the one side. You also mentioned Keystream. How does Keystream fit into the architecture of my device, and what's its relationship between the device, the service, and the customer's cloud that they're also implementing?
Yeah, so Keystream is actually the protocol handling the secure communication between your secure element through the host MCU and to your cloud application, or to the Keystream cloud, actually. So it is the framework, it is the baseline secure connection which is necessary for you to do all of the communication here. And then on the host MCU, you need the Keystream Trusted Agent, the KTA. This is a very small footprint software library running on your host MCU, which handles all the communication with the ECC 608 or TA 101 secure element, making sure that it generates the key correctly, do all the encryption, the handshakes with the Keystream cloud. Everything is ready to use. You don't have to do it on your own. Very easy to install it. So that makes life easier for any developer trying to implement a firmware over the air update capability. So if you did it on your own, then you know how hard and painful this can be. Here you get it for free. Use it.
Now, you mentioned there that the Keystream Trusted Agent for the host microcontroller is a small footprint, but the other aspect of this is also how much processing performance does it demand of the host microcontroller?
Oh, yes. So it is, talking about a footprint, it's about 5K in RAM and 13 kilobyte code size, more or less. It can run on constrained devices I don't have the exact data now for how much clock frequency you need for that, but I know from experience that it is capable of running on even small host MCUs. What, on the other hand, is important and necessary is that you have the capability of an immutable boot ROM, because this is the starting point, even in your host MCU, to make this root of trust fully capable of working, if you want to have the full security here.
Now, when my product's finished and been manufactured, it's going to disappear into a box, into a warehouse, and at some point, someone's going to buy that device and then want to start using it in a factory. It might be like a smart device for the home. Walk us through how that device becomes in a securely provisioned state once it's actually switched on in the field or at the customer's home.
Yeah. So once so we have Trust Manager, we have the ECC 608. It is in the sensor node. Microchip provisioned the secure element on our Microchip factory side. We shipped it to you. You installed it in your end product design, and now it's at the customer. So the first time the customer starts now the device or does the bootstrapping of it, then what happens is it connects via Keystream to the Keystream cloud and gets all the provisioning data it needs to run your application. So if you need a certificate, for instance, to connect to your manufacturer application, which resides in a cloud, for instance, AWS, then what happens is that the certificates needed for that will be pushed on the secure element on the host MCU, and then further processing can happen, such as key revocation, key rotation, or also adding other keys needed for a firmware update transaction, for instance. So a new update is available. Then what you need, or what you as a manufacturer do is you sign the firmware image with the private key residing in the Keystream cloud. And then you need to push the public part to your device securely. This happens via KTA as well.
And that sort of brings us almost back to the answers to the first couple of questions I had, because it seems there then that Trust Manager is mapping the lifecycle obligations of CRA to sort of these technical capabilities such as firmware updates, revocation of keys, adding keys, and so on.
Exactly. From a CRA standpoint, it's not mandatory to have updates, secure firmware over the air updates from the law. However, looking at the law and how you want to make it as convenient as possible for your clients, you of course want to have the capability to update the devices in field, and for that, sure, you want to go the easy way, the pathway which is less burden for you as a developer, and that's where Trust Manager comes into the game. Also, I forgot to mention that the Trust Manager and the ECC 608, they are host controller agnostic. This means today you go with Microchip, cool. Tomorrow you go with a different vendor, also okay. So you don't have to do the switch from the secure element also, but you can switch only the host controller. This gives you more flexibility in terms of how you would like to design your product in the future.
Well, thanks ever so much for that overview. I know personally, having worked on sort of cryptography solutions in the past for secure key fobs in the automotive field, that it's a very complicated, very difficult topic to do correctly and securely. And it's been great to talk to you and get some more details on how it's actually now going to be implemented to meet those CRA requirements.
Perfect, Stuart. It was a pleasure talking to you about the Trust Manager and how you can enable it in your designs. So looking forward to another meeting with you.
So that wraps it up for today. What have we learned about CRA and its implementation? I think it's fair to say that cybersecurity is still viewed by many in the industry as a painful, optional add-on that simply makes products perceived as low security risk more expensive. However, as embedded systems become more capable, hackers are increasingly using them as an easier entry point into otherwise secure systems. The Cyber Resilience Act requires us to address this issue properly, and it's now a non-negotiable for those seeking to enter the European market. Fortunately, as Tim's already explained, much of the complexity, such as public key infrastructure, doesn't need to be built by hand. Instead, hardware root of trust, such as the AT-ECC 608C, and managed services such as Trust Manager and Keystream can automate device onboarding, manage in-field provisioning, and securely handle over-the-air updates throughout the lifetime of your product. So my thanks go to Tim Scherer from Microchip for sharing his technical insights today. If you'd like to learn more about the CryptoAuth Pro Trust platform or Microchip's CRA solutions, follow the links in the description below. Thanks for watching, and we'll see you next time.